Imagine the most powerful explosion humanity has ever created. A nuclear blast capable of wiping out entire cities in seconds. Now picture unleashing that same force on the largest planet in our solar system. A world so massive that more than 1,000 Earths could fit inside it. A planet with no solid surface, only endless layers of swirling gas, crushing pressure, and raging storms that have lasted for centuries. This is Jupiter, a giant that dominates space with its immense size and mysterious nature. And today, we're exploring a fascinating question that sounds like science fiction, but is rooted in real physics. What would actually happen if a nuclear explosion occurred on Jupiter? At first, it might seem like such a blast would create a massive, planet-shaking explosion. Something so bright and powerful that it could be seen across the solar system. But the reality is far more complex and surprising. A nuclear explosion releases an incredible amount of energy in a very short time, producing intense heat, light, and a shockwave that can destroy everything nearby. But Jupiter is not like Earth, where explosions interact with solid ground and a relatively thin atmosphere. Instead, Jupiter is made mostly of hydrogen and helium, with clouds that stretch thousands of kilometers deep and pressures that increase dramatically as you go further down. If a nuclear weapon were detonated in Jupiter's upper atmosphere, the explosion would initially create a bright flash and a rapidly expanding fireball, heating the surrounding gases to extreme temperatures. But unlike on Earth, there would be no solid surface to reflect or amplify the blast. The energy would quickly spread out into the surrounding gas, and the fireball would begin to lose its intensity as it mixes with Jupiter's thick atmosphere. At the same time, Jupiter's immense gravity would play a major role, pulling the hot gases inward and preventing the explosion from expanding as freely as it would in space or on Earth. The shockwave, which on Earth can level cities, would travel through Jupiter's dense atmosphere, but would weaken much faster due to the sheer volume of gas absorbing the energy. Instead of causing widespread destruction, the explosion would likely create a temporary disturbance in the clouds, a brief and localized event that would fade relatively quickly. However, this is only the beginning of the story, because Jupiter is not just big, it is extreme in every sense. And as we go deeper into this scenario, the conditions become more intense, more unpredictable, and far more fascinating than you might expect, raising questions about whether even the most powerful weapons humanity can create could have any lasting impact on such a colossal world. As the initial flash of the explosion fades into Jupiter's vast and turbulent atmosphere, the true scale of the planet begins to reveal just how insignificant that burst of energy really is. Because while a nuclear explosion may seem unimaginably powerful on Earth, on Jupiter, it becomes something far smaller in comparison to the planet's natural forces. Jupiter's atmosphere is not calm or stable. It is constantly in motion, filled with jet streams that can reach speeds of hundreds of miles per hour, and massive storms that dwarf anything we have ever seen on Earth. The most famous of these is the Great Red Spot, a gigantic storm that has been raging for more than 300 years and is large enough to swallow Earth whole. And yet even this enormous storm is just one feature among many in Jupiter's chaotic atmosphere. When a nuclear explosion occurs within this environment, the surrounding gases would immediately begin to absorb and disperse the energy, with the heat from the blast quickly spreading into the colder layers of the atmosphere. Unlike on Earth, where the explosion would create a rising mushroom cloud due to differences in temperature and density, Jupiter's lack of a solid surface and its deep, dense atmosphere would prevent such a structure from forming in the same way. Instead, the heated gases would rise and mix with the surrounding clouds, creating a temporary disturbance that might appear as a bright, expanding spot when viewed from space. However, this spot would not last long, as Jupiter's powerful winds would stretch, twist, and eventually erase any visible traces of the explosion. Another important factor to consider is the immense pressure found within Jupiter's atmosphere, which increases rapidly as you move deeper into the planet. Even a short distance below the cloud tops, the pressure becomes so intense that it would begin to compress and contain the energy of the explosion, preventing it from spreading too far. This means that the deeper the explosion occurs, the less visible it would be from the outside, as the surrounding layers of gas would effectively trap and absorb the energy. In fact, if the explosion were to happen far enough below the surface clouds, it might not be visible at all, with all of its energy being dissipated internally, without creating any noticeable external effect. What makes this scenario even more intriguing is the comparison between the energy released by a nuclear explosion and the natural energy already present within Jupiter itself, because the planet continuously generates and radiates enormous amounts of heat due to gravitational compression and internal processes, meaning that even a powerful human-made explosion is tiny when placed against the backdrop of Jupiter's ongoing energy output, setting the stage for an even deeper exploration into whether anything we can create could ever truly disturb such a massive and powerful world. To truly understand just how small a nuclear explosion would be compared to Jupiter's natural power, we need to look deeper into the planet's internal structure and the incredible forces constantly at work beneath its cloud tops. Because Jupiter is not just a giant ball of gas floating quietly in space. It is a dynamic world driven by heat, pressure, and gravity on a scale that is almost impossible to imagine. Beneath the colorful bands of clouds lies layer after layer of increasingly dense hydrogen. And as you descend further, that hydrogen begins to behave in ways that defy everyday experience, eventually transforming into a strange state known as liquid metallic hydrogen, a substance that can conduct electricity and is believed to play a key role in generating Jupiter's massive magnetic field. This internal region is under such extreme pressure that it produces enormous amounts of energy, and in fact, Jupiter emits more heat than it receives from the Sun, meaning the planet is constantly releasing energy from within itself. When you compare this natural output to the energy of a nuclear explosion, even the most powerful bombs ever created by humans become almost insignificant, like a tiny spark in the middle of a raging storm. If a nuclear explosion were to occur on or within Jupiter, the energy released would be quickly overwhelmed by the surrounding environment, absorbed and distributed through the planet's vast layers without causing any lasting disruption. Even if multiple explosions were detonated at once, their combined energy would still be minuscule compared to the forces already present inside Jupiter, and the planet would continue its processes as if nothing had happened. Another fascinating aspect to consider is Jupiter's immense magnetic field, which is the strongest of any planet in our solar system and extends millions of kilometers into space, trapping charged particles and creating intense radiation belts around the planet. While a nuclear explosion produces electromagnetic effects, including a burst known as an electromagnetic pulse, Jupiter's magnetic environment is so powerful and complex that it would easily dominate and overshadow any such effects, preventing them from having any meaningful influence on the planet as a whole. At the same time, the explosion's radiation would be rapidly diluted within Jupiter's thick atmosphere, further reducing its impact and ensuring that it remains a localized and temporary event. All of these factors point to a surprising conclusion that challenges our intuition. Because while nuclear explosions are among the most destructive forces humanity has ever harnessed, they are simply not powerful enough to compete with the scale and intensity of Jupiter's natural systems. And as we continue exploring this scenario, an even more intriguing question begins to emerge, not just about what happens immediately after the explosion, but whether there could be any hidden or delayed effects that might unfold over time within this immense and mysterious planet. But what if the story did not end with the immediate effects of the explosion, and instead something more subtle and delayed began to unfold deep within Jupiter's vast atmosphere, hidden beneath layers of clouds, where no direct observation could easily reveal the truth? Because, while the initial blast may seem insignificant compared to the planet's enormous scale, the idea of triggering a chain of reactions or disturbances over time introduces a new level of suspense to this scenario. Jupiter's atmosphere is not just a passive environment. It is a complex system driven by heat, rotation, and chemical interactions, where even small changes can sometimes evolve into larger patterns due to the planet's rapid rotation and powerful convection currents. If a nuclear explosion were to inject a sudden burst of heat and energy into a specific region, it could potentially disturb the local balance of gases, causing shifts in temperature, pressure, and motion that might slowly spread outward. These disturbances could be carried by Jupiter's intense jet streams, stretching across thousands of kilometers and interacting with other atmospheric features, possibly altering cloud formations or temporarily intensifying nearby storms. However, even in this more dramatic possibility, the scale of Jupiter continues to dominate the outcome, because any disturbance created by the explosion would still be competing against forces that are far larger and more powerful. The planet's rapid rotation, which completes a full spin in just under 10 hours, creates strong Coriolis forces that shape and stabilize its atmospheric bands, meaning that any injected energy would quickly be redistributed and absorbed into these existing patterns. At the same time, Jupiter's immense gravity would continue to compress and stabilize the atmosphere, preventing any runaway reactions from spiraling out of control. There is also the question of whether such an explosion could ignite Jupiter's hydrogen-rich atmosphere, a concept often imagined in science fiction, but in reality, this is extremely unlikely, because nuclear explosions do not create the sustained conditions necessary for large-scale fusion reactions, and Jupiter lacks the critical mass and core temperature required to behave like a star. Instead, the hydrogen and helium gases would remain largely unaffected beyond the immediate area of the blast, further reinforcing the idea that no catastrophic chain reaction would occur. Even if we imagine multiple explosions happening over time, the planet's natural systems would continue to absorb and neutralize these disturbances, smoothing them out as part of its ongoing atmospheric dynamics. This creates an interesting contrast between expectation and reality, where something that feels like it should have massive consequences instead becomes just another fleeting event in a world defined by extremes, leaving us to consider not only the limits of human-made power, but also the incredible resilience and stability of planetary systems on a scale far beyond our everyday experience. As we move closer to the final understanding of this scenario, the bigger picture becomes impossible to ignore, because what initially felt like a dramatic and potentially planet-altering event now reveals itself as something surprisingly minor when placed against the immense scale of Jupiter, a world where energy flows continuously at levels far beyond anything humanity can currently produce. Jupiter's storms, radiation, gravity, and internal heat are not just powerful, they are constant, shaping the planet every second without pause. And this continuous activity makes any single brief event, like a nuclear explosion, fade into near insignificance. Even the visual impact, which might seem like the most noticeable effect from a distance, would likely be short-lived, perhaps appearing as a bright flash or a temporary scar in the cloud tops before being stretched and erased by the planet's powerful winds. Over time, the atmosphere would return to its natural patterns, leaving no clear evidence that anything unusual had occurred. This leads to an important realization about the difference between human perception and cosmic reality. Because on Earth, nuclear explosions represent one of the most extreme forces we can imagine, capable of reshaping landscapes and causing lasting consequences. But in the context of a gas giant like Jupiter, they are simply too small to matter in any meaningful way. Scientists have long studied Jupiter to understand its structure, composition, and behavior, using data from space missions and telescopes to uncover the secrets hidden beneath its clouds. And these studies consistently show that the planet operates on scales of pressure, temperature, and energy that dwarf our most powerful technologies. The idea of trying to significantly impact such a world with a nuclear explosion highlights the limitations of our current capabilities and reminds us of how vast and powerful the universe truly is. It also raises deeper questions about what it would take to meaningfully alter a planet like Jupiter, and whether any technology could ever reach that level of influence. At the same time, this scenario sparks curiosity and wonder, encouraging us to think beyond our everyday experiences and explore the boundaries of science and imagination. Jupiter becomes not just a subject of study, but a symbol of the incredible forces that exist beyond our world, forces that continue to challenge our understanding and inspire further exploration. As we reflect on everything we have explored so far, one final thought remains, bringing together all the science, speculation, and curiosity into a clear and meaningful conclusion about what this extraordinary scenario truly teaches us. In the end, the idea of detonating a nuclear explosion on Jupiter transforms from a dramatic thought experiment into a powerful lesson about scale, perspective, and the limits of human technology when compared to the vast forces of the universe. Because while such an explosion represents one of the most destructive capabilities ever created by humanity, it simply cannot compete with the immense size, energy, and complexity of a planet like Jupiter. What begins as a question filled with intensity and curiosity ultimately leads to a humbling realization that even our most powerful tools are incredibly small when placed against the backdrop of cosmic phenomena, where planets, stars, and galaxies operate on levels that are almost beyond comprehension. Jupiter, with its endless storms, crushing pressures, and powerful magnetic field, would barely register the impact of a nuclear explosion, quickly absorbing and dispersing the energy as part of its natural processes, leaving behind little to no lasting evidence of the event. This conclusion challenges our instincts and reshapes our understanding, showing us that power is relative and that context matters more than raw force alone. It also highlights the importance of scientific thinking, as only through physics, observation, and research can we truly understand how such a scenario would unfold, separating realistic outcomes from the dramatic expectations often seen in fiction. At the same time, this exploration serves as a reminder of why we study space in the first place, not just to answer questions, but to expand our perspective and deepen our appreciation for the universe we are a part of. Every hypothetical scenario like this opens the door to new insights, helping us learn more about planetary science, energy, and the fundamental laws that govern everything around us. As we continue to explore and push the boundaries of knowledge, questions like this will keep inspiring curiosity and imagination, driving us to look further and think bigger than ever before. And if you are benefiting from our topics, please subscribe, like, and turn on the bell notification so you can see our new videos early.